Hello, everyone. Let's start today's class. This is lecture number 6, and the topics that we will cover today are recursion and dictionaries. So last time we talked about two compound data types, tuples and lists, um, and um, and the difference between both of them is that tuples are immutable while lists are mutable, which means once we define a tuple, we cannot change its values individually within it. Whereas in lists, we can do that. And that has an impact on the concept of aliasing and cloning. Cloning is making a copy, while aliasing is defining another variable that points exactly to the other variable to which we assign it and points to the same physical items in memory. This mutability concept has side effects, and we looked at a few examples last time. What we will discuss today is another type, another category of algorithms and method of implementation, and that concept is recursion. And after that, we will talk about dictionaries, which is the third compound data type, and slightly different from lists and tuples. And like lists, this is also mutable, which means we can change the values within a dictionary as we use it in our code. So the definition of recursion, if you search it on the internet, it's a process of repeating itself in a self-similar way. So what does that actually mean? It means it reduces the problem in to a subset of the original problem and tries to resolve to solve it until we reach a base case. So here's a little example that how many twists does it take to screw in a light bulb? A recursive solution would be that you check whether it's already screwed in. If it is, then the answer is 0. No more turns. But if not, then twist it once and do it all over again, and add 1 to the answer. So you keep on doing exactly the same action, and every time you are doing one operation to add 1 twist to your answer, and keep on doing it until you reach this base case, which is that it's finally screwed in. Okay. How does this relate to programming? So an abstract way of defining the same concept in programming is that we divide and conquer, or we decrease and conquer. We decrease our problem set into a subset of itself and try to solve that. We keep on doing it, making it smaller and smaller until we reach a very simple case which has a very direct answer. And we will take a look at few examples in a few minutes. So how does that work in a program when we are coding? So this is so for example, there is a function which we have implemented as a recursive function. It has some base case and then some calculation. So what it does is it calls itself, and in every subsequent call, it reduces the size of the input by some logical method. Okay, and it keeps on doing it until it reaches a base case, which may be more than one, but every one of those base cases does not call the function itself. What it does is it returns a value, and then the unfolding of that recursive call in the scope happens, and it keeps on going back until it reaches back to the original caller, and all of these individual return values using this original base case results into some answer over here. So far we have only looked at iterative algorithms. Remember, using for loops and while loops for solving problems. What we do is we define a certain set of variables called the state variables, and they either increment or decrement until we do a certain set of state actions, We keep on doing it again and again until a case is reached where either the initial definition of our iteration reaches its final state, or we reach a logical end as defined in while loop examples earlier. So here is an example of multiplying two numbers, and a times b, or a multiplied b, is simply adding a to itself b times. So if we try to implement an iterative solution for that, is we start, our loop starts at b, and it decreases every time. This I state variable will decrease every time until it becomes 0. And within that, what we will do is we will add 1 to the result, okay? Or add a to the result if a was the other parameter. And we will keep on doing it until b reaches 0, and whatever is the value of result at that time would be the answer of a times b, okay? And here is a simple implementation. We say that multiply iteratively. This is the definition of the function. And what it's doing is it receives two numbers, a and b. It initializes the result variable as 0, and it says while b is greater than 0, do something. And what it's doing is it's adding a into the result, incrementing result with the amount of a, and then decreasing b by 1. So every time it goes back, b is 1 less than what it was before the previous iteration. And as a result, when we come out of this loop, our result has the value of a being added b times. And that's the iterative solution for multiplication. If we look at this in a recursive solution manner, what's happening is that we are saying a times b is equal to add a b times, okay? Which is which is exactly same as adding a to a times b minus 1. We took one a out of this multiplication. And this was our original problem. And this is what we have converted into one simple addition and the similar problem with which we started. But it's a little bit smaller than the previous one, okay? And we can keep on doing it. Next time, if we do it once again, the next step would be a plus a times b minus 2. And we can keep on doing this until we reach some base state, and that would be the recursive solution to the same problem. So this is our recursive reduction for the original problem of reducing it into one addition step, and then exactly the same kind of problem that we had in the beginning. So let's see how a recursive implementation of multiplication would look like. So we say multiply a with b. Now this is our base case, that if b is equal to 1, then just return a. And this is our recursive step, that if not, then return a plus, again call the same multiplication function with a and b minus 1. So this call will keep on going until b becomes 1, because we are decreasing it every time. And when it becomes 1, it's just returning a. And on each subsequent call, this is being added to the previous answer. Okay, and that would result in an answer which is the multiplication of a and b. So this is the concept of recursion, of calling the function calling itself with the slightly reduced problem. Factorial is another very interesting calculation. It's represented by n exclamation mark, and the mathematical answer to this is that n multiplied by n minus 1 multiplied by n minus 2, and so on, all the way when it becomes 1. the multiplication of all of these numbers is represented by n factorial. Okay. So what could be our base case in this scenario? We know that if n is equal to 1, the answer is 1. Okay. Because 1 multiplied by we have to go down only to 1, because if we multiply with 0, the whole answer would become 0. So this is our base case, that if n is equal to 1, then return 1. Then how do we reduce the problem? Rewriting it in terms of the original problem, but reducing its size. So n factorial is exactly equal to n times the factorial of n minus 1. Okay. Now this problem set, n minus 1 factorial, is same problem as n factorial. It's just one number smaller than that. Okay. So if our base case was if n is equal to 1, then return 1, then the else portion of that would be that n times factorial of n minus 1. And that would be our recursive step for this calculation. Okay. And the result of all of this multiple calls to the same function with the reduced problem set would result in the value that is finally returned to the user is n factorial. Let's see how this works in function scope that we saw previously. So here is the same function, factorial of n. If n is 1, return 1, else return n times factorial of n minus 1. Okay, and we are trying to find it for the number 4. Okay, so what happens is that when this statement is executed, within the global scope, this function is defined that has some code, and we are calling print of factorial 4. So when we call fact 4, it goes in here, it says whether it's 1, no. So it says return 4 times fact of 3. Okay, so another call is defined. So this is the first call when this print statement was executed, 4 times factorial of 3. And when this is executed, we call return 3 times factorial of 2, because the parameter this time was 3. And when this function is called, same function is called with the argument of 2, it calls once again, and it says return 2 times factorial of 1. And when this is called with the value of 1, we enter the base case. Okay. And the result of that is it's returning 1 back. Okay, so 1 is returned back to the previous call, which says return 2 times whatever was returned here, which is 1. So the value of 2 times 1 would be 1. And this will keep on going back the way it came forward. This would be a value of 2 is being returned back. So this would be returning 3 times 2. Here, the value of 6 will be returned. So, and it's asking 4 times whatever is returned back to me from this call. 4 times 6 comes back here. So factorial of 4 will eventually, through these recursive calls, will result into the answer of 24, which is the right answer. So this is how the recursive calls work, and the same function is being called again and again. But it is being called by one less number because we are decreasing its size here in this call. So, so what's happening here? So each recursive call, as we saw here, is a scope by itself. So whether the variable name is same or not, it doesn't matter, because within each scope, we have a new variable n with a different value. So these are not aliases. These are new variables in each subsequent recursive call, and the flow of control passes back to the previous scope once the current one ends, either in a return statement, or it would only end in a return statement. Otherwise, it would call itself with a smaller subset in any case. Okay. So here's the comparison of the iterative implementation of factorial and a recursive implementation of factorial. So in the iterative solution, it receives the same number n. It is receiving a number n here. Here we have to keep track of the product, and we say that this loop will run from 1 to n plus 1 because this range function always ends at this value minus 1. So it would use the value of I from 1 all the way to n. And it's doing this. Here we have the formula that product is equal to product times I. And when we come out of this for loop, this product would have the factorial value. Okay. But if you look at this implementation, it looks a lot cleaner and a lot more intuitive. That we are saying factorial n. If n is 1, then the factorial value is 1. If not, then the factorial value is n times factorial of n minus 1. And that's all we have to do in this recursive implementation. And it's a lot more easy to understand when we read it as compared to trying to understand what's happening here in the iterative solution. Right? So it's simpler, more intuitive. And also from the programming perspective, it also may be efficient. Okay. But from a computer's perspective, it might not be, because every time it's creating a new scope, there may be more memory being used. But from a programming perspective, it's intuitive and efficient. Okay. So why does it work? If we have to look at a proof of why recursion always work. The reason for that is in this example, for example, they are both implemented in a way that they are expecting the value of b to be a positive integer. We'll have to modify the solution, both of them, if we want to accommodate negative integers as the inputs. But in any case, the way it works or why it works is because of the concept of mathematical induction. Okay, or we can say the other way around, that mathematical induction method of proving something can be used to prove that recursion would work for our scenario. Okay, so the way mathematical induction works is that to prove that any statement which is indexed on integers is true for all values of n, the way induction works is that we first prove that it is true for the smallest value of n, because there's always a range for these kind of scenarios. And then we try to prove that if it is true for any arbitrary value of n, and using that new formula, we try to deduce using algebra to show that it is also true for n minus n plus 1. Then it must be true for any value, infinite number of values of n. That's how induction simply works. Here's an example. For example, we say that if we have to add all the numbers from 0 all the way to n, then the answer is n into n plus 1 divided by 2. Okay, so this is our statement. But how do we prove it? We say that if n is equal to 0, then this formula, all of it, 0 times something divided by 2 is 0. Okay, so 0 is equal to 0, which is true, and this would be our base case. And then we say, okay, let's assume that it is true for some value of k. So within our formula, we say that, okay, let's assume that it is true for these values. And if we can also prove that this is also true, then the answer should be n into n plus 1. So k plus 1 into k plus 1 plus 1 divided by 2 should be equal to this statement over here. And using simple algebra, we can continue to simplify this, and eventually what we would reach, if we try to algebraically simplify this statement on the left-hand side, we would reach the same formula that we are looking for on the right-hand side. And that would be our proof. I would not do any more induction examples. This is not a maths class, but this is the mathematical proof of of why recursion works in programming as well. So relevance to our code is that we have exactly the same methodology that we try to use here. We say that there is a function, there is a mathematical calculation of multiplying a with b, and all we can use is the plus operator. We cannot use the multiplication operator directly to find the answer. Okay. And we say, okay, it's true for the base case, which is a. Then it should also be true for some arbitrary value k. And if it's true for k plus one, then we assume that the whole solution works. So every time what we are doing is we're reducing our problem set for this call by one number, and eventually we are getting to our answer. Okay. Um, Here's a very interesting problem, and you cannot solve or implement this solution iteratively. Either it would take a lot of lines of code, or probably it's not even possible. So let's take a look at this example of Towers of Hanoi. You might have heard of this. And the story is that there are three tall spikes and a stack of 64 different sized discs on them. And the monks are trying to move all of those 64 sized discs from one spike to another, to another spike. Okay. And if when they're done, the universe would end. So you might think that it's an easy task. They might do it very quickly, but the issue here is that they can only move one disk at a time, and the larger disk can never be on top of a smaller one. Okay. So let's see. Can you still see my screen? So this is a simple animation of this same problem. There are three spikes. We have three disks on one, and we are trying to move all of them to the one on the rightmost side. Okay. And the way it would work is it's not simply taking all of them, because we can move only one at a time. And we can also not put a smaller one on top of the larger one. Okay. So as we increase the number of spikes by one, the number of moves over here which are needed to perform the overall operation increase many times, the increase in our number of disks. If we do it with five, it would be exponentially more than what we needed for four. Okay. Uh, so how do we solve this in programming? If we think recursively, what we are doing here is we are solving a smaller problem, then we are solving a basic problem, and then a smaller problem. Okay. So what we are doing is, let's say, for these five disks to be moved, our smaller problem would be that move four of them to this area. And then our basic problem would be that move the fifth one to the right. And then another call to the smaller problem would be move these four disks back on the fifth one. Okay. How do we move those four disks? That's the smaller problem. Exactly same. The smaller problem over here is move these three to the middle, move the fourth one to the right, and then again a call to the smaller problem of moving the three that we put over here back on the fourth one. Okay. So how do we move those three? We move these two to the center and third one to the right, and then those two that we put here back on the third one. Okay. And we keep on doing this until our problem comes back to the basic case, which is just move one disk. Okay. So how do we solve this in programming in recursion? Here's a very simple piece of code which does this calculation for us of what needs to be done to move a number of spikes from one spike to another, a number of disks from one spike to another. So I have a print move function here, which simply says, which is just telling you it's moving from to the to spike. Okay, and here is my recursive definition for towers, and it's receiving an input. Okay, this is the number of disks. They are all sitting in from. They all have to go to 2, and I have a spare spike. Okay. If there is only one disk, okay, then just print the move that you can simply move it from to 2. But if not, then leave the last one, and everything on top of that should be moved to spare. And once that's done, we have only one left, move it from to 2. And our last call would be then, okay, the ones that you put in spare, which are n-1 disks, move them from spare to 2. And that would solve our problem of moving everything. And this simple piece of code does all of that. That it's calling itself to solve a smaller problem twice in here, because we have to move them to a spare spike and then from spare back to 2. And between those two, we are moving the largest one, which was only 1, using our base case, from the from spike to the to spike. Okay. Let's take a look at its implementation. Okay. Exactly same function, and I'm calling it with the 4 disks and calling the spikes P1, P2, and P3. Okay. And this is the number of steps that it has to do, and this is exactly the same same animation that we saw here. That if we have 4 disks, we would need 15 moves. And over here, if we count all of these lines, they are 15 moves. And as I said earlier, the increase in this problem set is exponential when we talk about complexity in some future lecture. In some future lecture, when we talk about complexity, you would see that this, with 3 disks, our number of moves is small. It's 1, 2, 3, 4, 5, 6, 7. And by increasing the size by only one number, our number of moves become almost double. And if I have 5 disks, the number of moves would be quite large. And that's why this is one of the complexity wise, this is one of the very difficult or time consuming algorithms. And that's why those 64 disks are in no one's lifetime they would be done with their moves. Okay. So so far we have seen that there is only one base case. Over here we have one base case. In multiplication we had one base case, but there are problems where we have more than one base cases. Let's take a look at that. So Leonardo of Pisa, also known as Fibonacci. All of you must have read about Fibonacci numbers in mathematics. He told a challenge to everyone for some calculation. He said that a newborn pair of rabbits, one male and one female, are put somewhere together in a cage, and it takes 1 month for them to mature, and then it takes 1 month of gestation period for giving birth to a pair of rabbits. And every time they give birth to 2 rabbits, when they do, one of them is male and one of them is female. And so for the first pair, that would happen on the end of 2nd month. And he said that how many female rabbits would be there at the end of 1 year, which is 12 iterations. Okay. And it's a very simple definition, but the calculation is a little bit tedious. This is month number 0. We have 2 small rabbits. After 1 month, they become mature. Another month passes and they give birth to a pair. 1 month after that, the older pair becomes mature, and the earlier one gives birth to two more rabbits. And this keeps on going every month. You can see that this is increasing, not as an integer, but with a slightly different value. Okay. So here's the simple illustration. These are the number of months. Our base cases are these two, 0 and 1, and both of them would be one rabbit each, okay, in each month. And then for each iteration, we are adding the previous two values to get the next one, okay? This plus this equal to this. And so in third month, we have 1 plus 2, which becomes 3. In fourth month, we have 2 plus 3, which becomes 5. And then in fifth month, we have 5 plus 8, 3 plus 5, which is 8. And then 5 plus 8, 13. So this sequence is known as the Fibonacci sequence or Fibonacci numbers. And the logic behind it is the story and the problem that I showed you with the rabbits. So let's see what we do, how we calculate that in programming. Our base cases are that in 0th iteration, the answer is 1. In the first iteration, the answer is 0. Answer is 1 again. And then for every subsequent, if it's not 0 and if it's not 1, the number for which we are trying to find Fibonacci, then the answer is that Fibonacci of n would be the sum of n minus 1, whatever was there in n minus 1, and whatever was there in n minus 2. And the sum of these two would be the Fibonacci number for n. Okay. And here's the very simple recursive implementation of this concept. We are assuming that x is an integer value greater than or equal to 0. And this is our base case, which is if x is equal to 0 or x is equal to 1, then return 1. If not, then use the same function and try to find the Fibonacci of x minus 1 and x minus 2, add them and return it. And this keeps on going for a large value of x. This keeps on going, keeps on calling itself twice in every call, and the resulting value would be the Fibonacci of this number x. So what happens so far? We have seen this recursive algorithm on acting on numbers, but there are scenarios where it can work on strings or any other kind of problem set. Finding whether a string is palindrome or not. Palindrome is a string that reads the same forwards and backwards. Okay. And here are some very famous palindromes, which are not very simple words or couple of words. Attributed to Napoleon, he said, "Able was I ere I saw Elba." Read this way or that way, if you remove all the punctuation marks and spaces, it would exactly be same. So the sequence of characters within this string is same going this way and that way. That makes it a palindrome. Here's a slightly larger one. If we rewrite, take out the question mark, the commas, and the spaces, and we look at the characters, if we read it this way, it's exactly same as if we are reading this way. So that makes it a palindrome. Okay. So how do we solve this using recursion? Our base case would be that if the string is empty, or if it is just one character, it is already a palindrome. Okay, because when we reverse it, nothing happens. It remains same. So that would be our base case. Okay. And what would be our recursive step in here? We look at the first one and the last one. And if they are equal, we say now check for this subset to be palindrome. Okay. And within that call, check, it would again do exactly the same operation. B is equal to B okay, then check this subset. And it will keep on doing it until it reaches somewhere here, either the center element, or if it is even number of characters, the last string would result in a 0 length string. And that would eventually, if none of these checks on every subsequent check of two end characters on the beginning, one in the beginning, one at the end, if none of these was false, and we reached our base case, the answer is that yes, it is a palindrome. Okay. It is a very simple recursive implementation. If you try to do it with an iterative implementation without recursion, it would be quite complex. But it has a very simple check. Okay. Check this and this. If they are equal, then check whether everything within it is still a palindrome. So keep on doing it. Keep on calling itself with a smaller subset every time, and the answer that you receive would be either true or false, which would tell you whether it's a palindrome or not. So let's take a look at this code in Spider. It's such simple. So our function is palindrome has two more functions in it. If one of them is simply doing the cleaning operation. It's removing all the spaces, punctuations, making it lowercase so that our comparison operator works. And our isPal function is doing the actual check. It says if the length is less than or equal to 1, then return true. If not, then check whether our element at the first place is same as the element at the last place, and whatever is left other than these two is also a palindrome, and just return that value. So this will keep on calling itself with a smaller subset of the string while checking the first and last characters, and until it reaches the length of s being passed to be less than or equal to 1, in which case it will return true. Otherwise it would end and return with a false value of this logical operation. Okay, if they are not equal here. Let's take a look in our code. Okay. So the first parameter that we are passing it is EVE, Eve, and it is a palindrome. So the answer is true here for this function call is palindrome. The second one is the same example as I showed you in the slide. It is also a palindrome, so the answer is true. Is this a palindrome? No, it's not. We can simply see the characters don't match on either end. Okay, and the return value from the same function that we just saw on the slide is false. And it is quite simple, 4 lines of implementation that does all of this calculation for us. Okay, let's move on. So so this method is called a divide and conquer method. So what we are doing is we are breaking our bigger problem into a sub problem with a slightly smaller version of the same problem, and we keep on doing that until we reach a base case. And the solution for the smaller problem defines whether our larger one can be solved or not, or contains the answer or not. And that is the divide and conquer concept that we use in our recursive implementations. Okay. Before we finish, coming to the second part of this lecture, which is the introduction to third compound data type called dictionaries. So earlier, what we saw in definition of tuples and lists is that they have values like an array. So let's directly take a look at this example that we have some students, and we have a list of the names of those students. Okay, there we have 4 over here. Then we have their grades defined in another list. So the first grade would point to the first student, second grade would point to the second student, and so on. And then we have another third list which contains the code of the course that they are taking. Okay, so first one would point to the first student, second one would point to the second student, and so on. So if we try to maintain data in our programs this way using lists, we have to, and it's interrelated data. Okay, this name has this grade and is going to this course. This name has this grade and is going to this course. Okay, so we have to maintain a separate list for each of these sets of data, and then each list must be of same length, so that we can match these elements. Okay, and the information is stored in multiple variables, and the only relationship between them is that the same index over here has a related item in the same index in the other list. Is there a better way of maintaining this kind of data or storing this kind of data? Okay, and the update and retrieval for this would also be a little bit tedious. If we say, okay, get grade for this student, and we have to pass it all three lists, the name list, the grade list, and the course list. Okay, and all it is doing is getting an index for finding the name of this student from the name list, and then using the same index to find the item in the grade and course lists, and then returning it as a tuple over here. Okay. So this becomes quite messy if you have a lot of data, a lot of different types of data, but they're all interrelated with each other. Let's take a look at how we can use dictionaries to make it a little bit easier. Okay, so in list, our index is an integer, and we have the values at those indexes. But in a dictionary, we have replaced the index, or Python has replaced the index with a label, and it calls it a key. And then in front of that key, there is a value, and this value can be anything. It can be one of those scalar values of integer, float, or string, but it can also be a collection or another compound value. Okay, so we can say, okay, this student has all the information in front of it, and by student name as the label, we can access that data very easily. So here is an example. So here's the definition of the dictionary, and it is unlike tuples were defined by parentheses, lists were defined by square brackets. So a dictionary is defined by curly braces, and the definition or the values are that this key has this value, this key has this value, and this is defined by the colon between them. Okay, but we can define it in a loop or in another way as well, and we will take a look at that code. So this, after we run this these two statements, somewhere in the memory we have this data, that in front of a name there is a grade, in front of this name there is a grade. Okay, and it's much more intuitive than maintaining multiple lists like this. Okay, so same table. If we say this name has this grade and so on. Okay, and we say, okay, get me within grades, get me whatever is in front of Hanan, and the answer would be A. This is because Hanan is pointing to the grade A. If we try to get the grade of a name that is not present here, we would get a key error, because this is the key that it is trying to find in this dictionary. Okay. So it's very simple to get the answer from a dictionary. All we have to do is provide it with this label, and we would get the answer back. Okay, let's say we have a definition, 4 names and their grades, and we add an entry by saying grades sub econ is equal to A. What that would do is add this entry over here in this table. Okay, now we can test if a key is in a dictionary, and the way to do is this statement, Hanan in grades. This is a logical operation, and this would return you either a true or a false. Since Hanan is present in our dictionary over here, this statement of Hanan in grades would return a true value. While if I say Mohit in grades, it would return a false value. All right. Another operation on dictionary is deleting an entry. If we had an entry over here and we say delete grade sub Humayun, it would remove whatever label I asked it to remove. Okay. What other operations can we do? Let's say we want to iterate over them. Okay. There are these two functions of this grades or dictionary data type. On this object, we can say, okay, get me all of the keys. And this would return an array or an iterable data type through on which we can iterate with all the keys over here. And I can also say, get me all the values from this grades dictionary. That would return me all of these values. Okay. And we can use these two functions in our loops and our checks. I will show a couple of examples. So values can be any type, immutable and mutable, both. There can be duplicate values. For example, in our example, we have two students with the same grade. And these values can be lists or even other dictionaries. So you can have multi-level or nested dictionaries where the value of one element within a dictionary is another dictionary. The keys, however, must be unique so that we can search them, we can change their value, and they are usually immutable, so that we don't get into any kind of logical issues. And the reason for that is that we need an object that is hashable. We won't go into the detail, but for searching on a dictionary by using the label, we need something which is searchable. And hashable is another word of a little bit complicated topic at the back end, but it makes it easier to search through dictionaries. With float types as key, you have to be very careful, because if it has a lot of decimal places, and in our calculation we are not using the same number of decimal places, if it becomes a key, you might get issues by for identifying them. For the storage of a dictionary at the back end or in the memory, there is no order of keys or values. But every time you look for a key, its value would certainly be returned to you. Some similarities and differences. They are both. So list is a sequence of elements, whereas in dictionary we have keys and values. When we get an element from a list, we provide it an index, whereas in a dictionary we look up the item by using the key. Okay. Indices within a list have an order, like they start with 0 and go all the way to n. In a dictionary, the way it is stored internally in the memory, there is no order guaranteed, and there is no need for that order to be there. Index is always an integer for a list, but keys can be any value of an immutable type. Okay, now let's take a look at a coding example of a dictionary. We say we have a song, we have lyrics from a song, which we feed to a dictionary. And then what we are trying to find is we are trying to find how many times which word occurred. Okay, and that calculation we can easily do with a couple of loops and using dictionaries. And then we can also use the same dictionary and write a slightly different function to find find all the words that occur more than a certain number of frequency. Okay. Let's take a look at this piece of code. We say lyrics to frequencies. It gets a string of lyrics and creates a dictionary. And it says for word in lyrics, if the word is already present in my dictionary, then increase its frequency by 1. If it's not present in my dictionary, then add it to the dictionary with the frequency of 1, which means as we go through the lyrics, this was the first occurrence of that word that we came across. And it would return this my dictionary. So this function simply is converting our lyrics into a dictionary with the word as the key and the number of times it appears overall in the song as the value in front of that word. Okay. Our function for finding most common words, if we created this dictionary here and we feed that dictionary as frequencies to this function called most common words. So we are trying to find most common words or the word with the highest frequency as a result. Okay, so we say put all the values, which are all the numbers of occurrences of each word, into a variable called values by using this dot values function. And then we use this max function on this list of integers and this gives us the highest frequency or the best word within the lyrics. And then we define an empty list, and we say for k in frequencies, if frequencies sub k is equal to best, then and best is the highest frequency that we already calculated, then append this word into our list that we created words. So as a result of this overall function, what would be returned back to us is that these words are the best words, which means these words have the highest frequency within this overall song implementation. And then we have another function which we can give it our dictionary of frequencies and give it another parameter called minimum times. For example, we say give me all the words that occur more than 10 times in this song. And this implementation would look for that using this minimum times being compared with the value of the frequency while going through the frequencies, and keeps on adding those words to this result array, and eventually it would return it. Okay. Let's take a look at the implementation of all of these functions here. This long set of code does that for us. Okay. And here is the frequency that U occurs 36 times, Ya occurs 28 times. And this is the result of calling words often from the Beatles dictionary, which was defined by these lyrics. And we asked everything that occurred more than 5 times, give me that number. If I ask, give me words which are often used, but more than 10 times, the result would be slightly lesser than the previous dictionary. So these kind of operations we can do, and using dictionaries make these very, very easy for us. Last item that we will look at today is making the recursive code for Fibonacci that we looked at is if it is 1, if n is 1, then return 1. If n is 2, return 2. These are two base cases for us. If not, then calculate the Fibonacci of n minus 1 and add it to the Fibonacci of n minus 2 by calculating both of them. Okay. So within its implementation, the Fibonacci function calls itself twice. Okay. and it has two base cases. This code is inefficient. Why? Because for Fibonacci of 5, we have to calculate Fibonacci of 4 and 3. For Fibonacci of 4, we have to calculate Fibonacci of 3 and 2. For Fibonacci of 3, we have to calculate Fibonacci of 2 and 1, which are both base cases, so it would start returning from here. 2 is also a base case, so it would backtrack. But for Fibonacci of 3, it would again calculate Fibonacci of 2 and 1. But notice here that these values we have already calculated. Okay, if we traverse through the left side of the tree first. This 3 was already calculated here. This 2 was already calculated here. For the third time, we are calculating 2 again. And this Fibonacci of 1 was being calculated over here. Okay. So can we make our implementation of Fibonacci a little bit efficient? And the reason for doing that is it takes a lot of time to calculate Fibonacci numbers if the numbers become slightly larger. Okay. And let's see, if I have this simple implementation of Fibonacci and I execute this, I have this function in memory now. And if I say, give me fib of 5, we know it's a small number 8. But if I call it with the number 50, let's see how much time it takes. It's taking quite a bit of time. And for a computer to take that much time to calculate something, it means our algorithm is really not very efficient. Okay. And it's still, while I'm talking since then, it's still trying to calculate it. Okay. I'll break it here and I'll try to calculate for, let's say, 35. It might come back in a reasonable time, but between 35 and 50, the time difference was that much that this still came back, but 50, we kept on waiting and it wasn't coming back. And the reason for that is that our inefficient implementation of Fibonacci numbers is doing a lot of calculations again and again. Okay, so let's try to use dictionaries and make our implementation of Fibonacci a little bit more efficient so that we don't have to, whatever we have calculated once, let's not calculate it again. Okay. So we say another function, Fibonacci efficient. It is trying to calculate the Fibonacci for n, but it also is receiving a dictionary. And dictionary contains everything that we have already calculated Fibonacci for. Okay. So first thing we check is that whether if n is already in the dictionary, then return whatever that value was. Don't calculate it again. But if it wasn't in the dictionary, which means that we have not calculated that value of n before, then the answer is call the same function with n minus 1 and n minus 2 and pass it the same dictionary. All right. But at the same time, once we have done this calculation, it comes back from here, then to the dictionary, add this answer on the label of n. So d sub n would contain this answer next time we come around this same problem. Okay, and then return the answer. Okay, we start with the two base cases already in the dictionary, so that this becomes our base case. So Fibonacci of 1 is 1, Fibonacci of 2 is 2, and then we try to calculate Fibonacci of 6. Okay, let's do the same calculation. Let's say fib underscore efficient of 6. If I can spell it correctly, I have to pass it B as well. That we defined on the left side, you can see it's 1:1 and 2:2. So I get an answer of 13. If you remember, when we used our previous function for calculating 34, it took a bit of time. And if I do this for 40, it's taking a considerable amount of time. Okay. But if I call my Fibonacci efficient, I broke it here with Control C, and I say, I want to calculate Fibonacci efficient for 40. Right away I get an answer because I'm not doing all of those multiple calculations for Fibonacci for the numbers that I have already done. If you remember that we called Fibonacci for 50, it wasn't returning any value back. But if I use Fibonacci efficient, I get an answer right away. In terms of the complexity or number of values, number of calculations that it does, it is quite a large amount of difference in number of calculations. If we use the regular Fibonacci call, recursive solution, but not storing the values that we have calculated every time, we are making the call to Fibonacci function more than 11 million times. But for the same number, 34, if we use our efficient calculation or call, we are doing only 65 individual calculations. So that's how using pre-calculated values in a dictionary, incorporating that into our recursive solution can have a major impact on the complexity of our solution. Okay. That would be the end of this lecture today. I hope you have enjoyed it. It was a little bit tedious topic. I will upload the video and you can revisit this topic. The code file was provided to all of you. Try to run that and see how things work. You can use the trace ability within Python to see how code runs on a line by line basis. These are these buttons on top, and try to use them while keeping your variable explorer open. And that way you can see how things are changing as you go on the code line by line. So try to do that. All right. Thank you very much, everyone. Bye.